More than 2,000 years ago, in the Greek city of Syracuse, there lived a brilliant and rather forgetful thinker named Archimedes. As the story goes, one day the king gave him a very tricky problem. The king had a shiny new golden crown, but he was suspicious. Was it pure gold? Or had a sneaky goldsmith stolen some gold and mixed in cheap silver? Archimedes had to find out without breaking the beautiful crown. Impossible. He thought and thought. Gold and silver can weigh the same, but they have a different density. To catch the thief, Archimedes needed the exact volume of the crown. But a crown is a strange, bumpy shape. How could anyone measure that? Poor Archimedes was so puzzled that he decided to relax and take a bath. He climbed into the tub, still thinking hard, and splash! The water rose up and spilled over the sides. Suddenly, he froze. His body was pushing the water out of the way. Displacement. The higher the water rose, the more volume his body had. He could measure the crown the very same way, and finally prove if the gold was pure. Archimedes was so excited that he jumped out of the bath and ran down the street, with no clothes on, shouting, "Eureka! Eureka! I found it!" And that is how a warm bath revealed one significant scientific principle. In 1928, a scientist named Alexander Fleming was doing research in his laboratory in London. He was studying harmful bacteria. Before a short holiday, he left some dishes on his table. When Fleming came back, he observed something strange. One dish was contaminated with a green mold. But around this contaminated area, the bacteria could not grow. There was a clear, empty ring around the mold. Many people would clean the dish and forget it. Fleming did not. He observed the mold carefully and formed a hypothesis. His hypothesis was simple. Perhaps the mold produced a substance that killed bacteria. To test this idea, Fleming tried to isolate the substance. It was very difficult to isolate, but he identified it and gave it a name: penicillin. Years later, two scientists in Oxford, Howard Florey and Ernst Chain, continued the research. They subsequently demonstrated that penicillin could cure sick patients. Their experiments clearly demonstrated its power. This was a significant moment in the history of medicine. Today, many antibiotics are derived from that first discovery. Every year, medicines derived from Fleming's work save millions of lives. So remember, a contaminated dish, one careful observation, and a bold hypothesis changed the world. That is why this discovery is so significant, and why great scientists always observe, question, and test. In 1854, a terrible disease called cholera spread through a neighborhood in London. Many people became very sick, and no one knew why. At that time, most doctors believed the illness came from bad air. But one doctor named John Snow was not sure. He decided to investigate the problem carefully. He wanted real evidence, not just a popular opinion. Snow began to collect data. He walked through the streets and marked every case of illness on a map. Slowly, a clear pattern appeared. The sick people were not spread out evenly. Most of them lived very close to one water pump on Broad Street. This pattern was important. Snow investigated further and found that the families who drank from this pump became sick. People who drank other water stayed healthy. The evidence pointed to one source: the water itself. Snow showed his map to the local leaders. He asked them to remove the handle of the pump so no one could use it. Subsequently, the number of new cases fell. From this careful work, Snow could conclude that dirty water, not bad air, carried the disease. His data helped prevent future deaths. Today, John Snow is remembered as a founder of a significant science, the study of how disease spreads. 200 years ago, on the rocky coast of England, a young girl named Mary Anning made discoveries that would change science. Her family was poor, so she searched the cliffs for fossils to sell to visitors. But Mary was not just a collector. She observed the rocks with great care. As a young girl, she found something amazing: the ancient skeleton of a strange sea creature hidden in the stone for millions of years. At that time, most people did not understand fossils. The idea that an animal could become extinct, that it could disappear forever, was new and shocking. Mary's discoveries provided important evidence for this idea. She continued to search the dangerous cliffs. She found more specimens, and she learned to identify the bones with real skill. Scientists came to her for help because she could reveal what these ancient creatures looked like.
So flat.
Yet there was a problem. Mary was a poor woman, and at that time, women could not join scientific societies. Often, men received the credit for her work. Her huge contribution was not fully recognized. Today, that has changed. We now recognize Mary Anning as a brilliant scientist whose fossils helped reveal the ancient history of life on Earth. In 1831, a young British naturalist named Charles Darwin began a long voyage on a ship called the Beagle. For 5 years, he traveled the world and made careful observations of plants and animals. In 1835, the ship reached the Galapagos Islands, near South America. There, Darwin collected many small birds. He observed that the islands shared a similar environment, but the birds were not all the same. The birds looked alike in many ways, yet Darwin noticed an important variation. Their beaks were different. Some beaks were large and strong. Others were small and thin. This variation in the beaks was connected to the food on each island. At the time, Darwin did not understand the full meaning of this evidence.
Only later, back in England, did experts help him identify the birds as separate species.
Gradually, over many years, Darwin developed a powerful idea. He proposed that animals slowly adapt to their environment. A useful variation, such as a stronger beak, helps an animal survive. Subsequently, these helpful features passed to the next generation. In this way, over a very long time, species can evolve and change. Darwin's careful work provided important evidence for this theory. So remember, patient observation, a small variation, and years of thought can gradually change how we understand all life on Earth. More than 2,000 years ago, a Greek scholar named Eratosthenes did something incredible. Without leaving Egypt, he tried to measure the size of the whole Earth. He heard about an interesting detail. In one city, at noon on a certain day, the sun shone straight down a deep well. There was no shadow at all. But in another city, far to the north, a tall stick did cast a shadow at the very same time. Eratosthenes had a brilliant idea. If the Earth were flat, there would be no difference. The shadow proved the Earth's surface was curved, so he decided to calculate how big the Earth must be. First, he measured the angle of the shadow. Then he needed the distance between the two cities. Using these two numbers and some careful geometry, he could estimate the Earth's full size. Of course, he had to assume a few things. For example, that the Earth is a perfect ball. His method was not perfect. Yet his final estimate was approximately correct, remarkably close to the true size we know today. So remember, with a stick, a shadow, and clear thinking, one person calculated the size of our entire planet, long before anyone could travel around it. In the 1780s in Italy, a scientist named Luigi Galvani noticed something very strange. When he touched a dead frog's leg with metal, the leg suddenly jumped as if it were alive. Galvani was amazed. He formed a hypothesis. He believed the electricity came from inside the animal itself. He called it animal electricity. But another Italian scientist, Alessandro Volta, was not convinced. He disagreed with Galvani's idea. Volta had a different hypothesis. He thought the real source of the electricity was not the frog, but the two different metals touching each other. How could he prove it? Volta decided to remove the animal completely. Volta had demonstrated that his hypothesis was correct. The metals were the true source of the power. This device was the very first battery. For the first time, people could produce a reliable current of electricity whenever they needed it. He stacked discs of two different metals, one on top of another, with wet cloth between them. This simple tower produced a steady electric current with no frog at all. His invention was so significant that today we still measure electricity in volts, named in his honor. So remember, a scientific disagreement and one clever experiment gave the world its first battery. In the 1860s, science had a messy problem. Researchers had identified many chemical elements. The basic substances that make up everything. But no one knew how to organize them. A Russian scientist named Dmitry Mendeleev decided to solve this puzzle. He wrote each element on a card with its properties. Then he moved the cards around, again and again, searching for a hidden pattern. The story goes that the answer finally came to him in a dream. He saw that if he arranged the elements by their weight and their properties, a clear pattern appeared. He organized them into a simple table. But Mendeleev did something bold. His table had empty spaces, gaps. Instead of ignoring them, he made a brave claim. He said these gaps were elements that no one had discovered yet. He even predicted their exact properties. Years later, scientists found those missing elements. Their properties matched his predictions almost perfectly. This was strong evidence that his system was correct. Today, we call it the periodic table, and it hangs in science classrooms all over the world. So remember, by finding a pattern and bravely predicting the gaps, one scientist organized the building blocks of the entire universe. In the 1850s, the ocean kept people apart. A family in Europe and a son in America could only communicate by letter. Each letter traveled by ship, and the answer took about 10 days to arrive. Love, news, and business all moved slowly across the water. Some people dreamed of something faster. They wanted to connect two continents with a long cable under the sea. A cable that could transmit a message in minutes. But no one had ever done this. The ocean was deep and wide, and many believed it was impossible. It was a huge challenge. First, engineers had to design a special cable, thousands of kilometers long, strong enough to survive at the bottom of the sea. Then came an even harder question. How could one ship carry a cable long enough to cross the whole Atlantic? The answer was teamwork between two countries. One ship from Britain and one ship from America each carried half of the cable. They sailed to the middle of the ocean and carefully joined their two halves together. Then the two ships slowly sailed apart in opposite directions. One traveled toward Europe and the other toward America. Each ship placed its half of the cable on the ocean floor as it moved. Step by step, the line grew longer in both directions. In 1858, the first cable was finally finished. To celebrate, Queen Victoria sent a friendly message to the American president. But the cable was very weak, and this short message took many hours to transmit. A few weeks later, the signal died completely. People were disappointed, but they did not give up. Subsequently, they built a stronger cable. This time, the enormous ship Great Eastern, the largest in the world, was big enough to carry the entire cable alone. In 1866, it crossed the Atlantic, and the new cable finally worked. Finally, the impact was enormous. News that previously took 10 days could now connect two continents in just minutes. People could communicate across the ocean at last, and the whole world suddenly felt smaller. For thousands of years, humans dreamed of flying. In the early 1900s, that dream finally came true. But who did it first? Even today, people dispute the answer. In the United States, most people say the Wright brothers were first. In 1903, on a windy beach, their machine flew for the first time. It was a real, controlled flight. But there was a detail. Their machine needed a special rail to launch, and it flew far from any public witness. And it flew in front of a large, official audience. So who was truly first? The answer depends on your criteria. If first flight means simply leaving the ground in a controlled machine, the Wrights achieved it earlier. If it means a public flight, witnessed and verified, that took off without any help, then Santos Dumont has a strong claim. This is why the dispute continues. Both men were brilliant. Both contributed enormously to aviation. In Brazil and much of Europe, people give the honor to Alberto Santos Dumont. In 1906 in Paris, his aircraft, the 14 bis, took off using only its own power, with no rail to help it. Perhaps the real lesson is that a great achievement rarely belongs to one person alone. So remember, sometimes the word first depends entirely on how you define it, and history can have more than one hero. Have you ever wondered how a huge suspension bridge can hold thousands of cars without falling? The answer is a clever journey of weight. Let's follow that weight, step by step. First, cars and trucks press down on the road, called the deck. This creates a heavy load. Now, where does this load go? The deck told them. The deck hangs from many thin vertical cables. As a result, the weight of the deck pulls down on these cables. These vertical cables connect to two enormous main cables, which curve across the bridge. In turn, the load transfers into these main cables. The weight is now moving upward and outward. Next, the main cables pass over the top of two tall towers. The towers are very strong, so they can support this huge force and push it down into the ground. But the main cables still pull hard at each end. Therefore, engineers build massive concrete blocks, called anchors, to hold the cables firmly. The anchors resist the pull and keep everything stable. As a result of this design, the load does not stay in one place. It spreads through the whole structure, deck, cables, towers, and anchors, and finally into the earth. So remember, a suspension bridge is strong not because it is heavy, but because it transfers and distributes weight so cleverly.